Hello all. Today we will talk about exercise 8.41, spring and a cylinder. So for this question, I actually found an alternative method to doing force analysis. So today we'll talk about the second method that I found. So for the first method, obviously we can just list out the net force formulas. So you have F equals to ma, tau equals to I alpha, and then A equals to R alpha. This is the no slip condition, so that this cylinder doesn't slip. This is the net torque formula, and this is the net force. And obviously we can solve for A, which will allow us to get the frequency of this oscillation, because we have the formula x2 dot plus omega squared x equals to 0. So now let's see the second method. For the second method, let's use energy. There's no force that would cause energy to be not conserved here, because look, we have static friction, and what do we know about static friction? Well, we know that it doesn't do any work, and so we know that energy is conserved. Well, what does this mean? Well, it means that dE dt equals to 0. That means E doesn't change. The derivative of E with respect to time is 0. So now all we have to do is write out a formula for an expression for total energy, and then take its time derivative, and hopefully we can get some formula that looks like this. And we probably will. So let's try. E equals to half mv squared plus half I omega squared plus half kx squared. And let's switch up the notation here a bit, since we're working with derivatives later. Let's write v as dx dt and denote it as x dot. And so on, we can later denote a as x2 dot, which means second derivative of x with respect to time. And so let's rewrite this. We know that E equals to half m x dot squared plus half I omega squared. Well, what's I? In this question, it is a solid cylinder. So I cylinder, we know that it's half mr squared. And we know omega times r equals to v, because this is the no slip condition, otherwise the cylinder would slip. And so omega equals to v over r. And so omega squared equals to v squared over r squared. And so we can write half times half mr squared times v squared over r squared plus half kx squared. And then we get E equals to half mx dot squared plus a quarter. This cancels out. And then let's write v as x dot again. So a quarter mx dot squared plus half kx squared. And now let's try to take the time derivative, because now we'll get some of this formula that gives 0. And why do we know we can do that? Well, when we take the time derivative, we will have x dot terms left. And this term will yield an x dot term too, because of the chain rule. And this will just become 0. And so we know definitely we can cancel out the x dot term, which is velocity. And it is not something we want. And so let's try to take the time derivative. And just to make it more clear, I'm going to write it out. And keep in mind, x in this case represents the position of the cylinder. And so x is a function of t. And so the chain rule applies. This is really important. So dE dt is 0, as aforementioned. And what's d dt of half mx dot squared? Let's bring the power down first. So we have mx dot, and don't forget the chain rule. So we have times x2 dot, which represents the derivative of dx dt with respect to time because of the chain rule. And then we have plus, we bring the power down, we get half mx dot, and again, don't forget the chain rule. x2 dot plus, bring it down, we have kx, and don't forget the chain rule. So time derivative of x is dx dt, denoted as x dot. So x dot. And now let's cancel out the x dot term. And we get mx2 dot plus half mx2 dot plus kx equals to 0. Let's group the terms. This and this, we get 2 over 3 mx2 dot plus kx equals to 0. And remember, we're trying to get this formula to the form of x2 dot plus omega squared x equals to 0, because this is the standard form for oscillation. And depending on the type of oscillation, if it's a damped oscillation, we can always add a damped term of bx dot, or we can even add a driven force term if it's a driven oscillation. But that is for later. We will discuss that later. But just so you know, we need to get to this form because this is standard form for oscillation, and this omega here, this is the frequency, or rather, omega is the frequency. And so now let's try to do that. Let's try to remove the coefficient in front of x2 dot. So why don't we divide by 2 over 3m, 2 over 3m divided 2 times divide that. So then we would get x2 dot plus 2k over 3m x equals to 0. And so we know that omega squared is 2k over 3m, and so omega, the frequency, is square root 2k over 3m. And the question was asking for the frequency of the oscillation. And so that square root 2k over 3m is the answer to this question. Thank you for watching.